Welcome back everyone. Myself Sakshi from CSC department. Today I'm going to do the presentation on the topic insertion sort of the subject principles of. So first we'll know what is insertion sort. A simple sorting algorithm that builds a sorted list by inserting each element into the correct position in the sorted part of an array. When to use insertion sort? So we'll know what are the conditions to use insertion sort and where do we use it. First one, small data sets. Insertion sort shines when dealing with small datasets as its performance is relatively quick for fewer items. Nearly sorted data. If the data is already almost sorted, insertion sort can be very efficient in placing the remaining unsorted elements. So basically, insertion sort is nothing but rearranging the numbers or whatever it is in an ascending or descending order. So come on, let's go on depth into the insertion sort. It is a simple sorting algorithm that works by iteratively inserting each element of an unsorted list into its correct position in a second portion of the list. It is like sorting playing cards in your hands. You split the cards into the two groups, the sorted cards and the unsorted cards. Then you pick up a card from the unsorted group and put it in the right place in the sorted group. We start with second element of the array as first element in the array is assumed to be sorted. So you can go through the picture side. So there is an unsorted array in the first. So the first element is considered as the sorted array. So then in the second step, we go through the second array and we start solving it. So you can read the explanation here and go through the picture so you'll get it very clearly. Compare second element with the first element and check if the second element is smaller. Then swap it. Move to the third element and compare it with the first two elements and put as its correct position. Repeat until the entire way is sorted. So when you repeat into the 5 steps or 6 steps, so how much array is there? So that much time when you repeat it, the entire array is ordered in the ascending order or descending order. So now we'll study about the applications of insertion sort. Insertion sort is commonly used in situations where the list is small or nearly sorted. Simplicity and stability are important. Used as a subroutine in bucket sort. Can be useful when array is already almost sorted. Very few inversions. Since insertion sort is suitable for small sized arrays, it is used in hybrid sorting algorithms along with other efficient algorithms like quicksort and merge sort. When the subarray sizes become small, we switch to insertion sort in these recursive algorithms. For example, intro sort and temp sort use insertion sort. So let us see now how insertion sort works. Step 1. The first element is considered to be sorted. So as I said before, so go through that picture, you'll get to know again. So first element we'll think as it is sorted. Step 2. The second element is compared with the first and inserted in its correct position. The process continues for each element, comparing it with the sorted portion and inserting it in the right place. So here is a simple example for insertion sort. So there is an initial array 5, 1, 4, 2, 8. So they see there. So we'll assume the first as the sorted array. So we will go through the second array. So then we will compare it with the first array. Then it is replaced by the first array. So we go through the 4 to 5 steps. So how many arrays are there total? 5 arrays are there. So when we continuously do it for the 5 steps, at last we'll get the sorted array. So this is the way we rearrange the arrays in an ascending or descending order. Advantages of insertion sort. So there are totally 5 advantages of insertion sort. It is very simple and easy to implement. Stable sorting algorithm, efficient for small list and nearly sorted list. Space efficient as it is in place algorithm. Adaptive, the number of inversions is directly proportional to number of swaps. For example, no swapping happens for sorted array and it takes O of n time only. Disadvantages of insertion sort. So there is very less disadvantages for insertion sort. So it is very useful for us during the programs. So the first disadvantage is so for large data sets. So obviously when you have large data sets, you can't keep arranging each and every data sets. So it becomes a very slow process for you guys. So second one is inefficient for large lists. So it's nothing but the first one only. So it is very slow. You can't go through the large list or large data sets. No as efficient as other sorting algorithms. So other sorting algorithms, it's not very efficient comparatively to other sorting algorithms. Example, merge sort, quick sort for most cases. So merge sort and quick sort are comparatively very fast and very efficient comparatively to insertion sort. The complexity of insertion sort. The complexity means, so best case is O of n, and the average case is O of n to the power 2, and the worst case is O of n power 2. Best cases and worst case scenarios. So where do we find it best as a case? So when it is already sorted, so when we do it in a sorted order, and when it's like descending to ascending order, so in those cases it's really best. And the worst is reversed or sorted. So when it is reversed, when you have to do it reverse, it's really very worst. So here is a simple program for insertion sort. Key is equal to array of I. J is equal to I minus 1, where j is greater than or equal to 0, and key is greater than array of j. Array of j plus 1 is equal to array of j. J minus is equal to 1. Array of j plus 1 is equal to k. Return to array. So we'll continue it for the every array. So to get a sorted array, array is equal to 5, comma 1, comma 4, comma 2, comma 8. Sorted array is equal to insertion sort of array. Print sorted array. So here, with the help of these programs, simple programs, you can sort the array in a very helpful way. So here is a summary and conclusion. So first summary comes here. It's simple to and easy to understand and implement. So second one is efficient for small data sets and nearly sorted data. Third one, stable, maintains the order of equal elements. Thank you.